Hello, BC Calculus students. This is Mr. Johnson, and we're going to do section 6.5, which is on the average value of a function, or also known as the mean value for integrals. As a quick review, if we look back to chapter 4, the mean value theorem for derivatives is sort of connected to this, but this is for integrals. But the mean value theorem for derivatives says that if you have this function f of x, and it is continuous and differentiable, then on an interval, let's say it's a to b, you can calculate the slope on this interval, and that slope would be f of b minus f of a, and divide that by b minus a, which is equal to the derivative of this function at some value c. So there's an instantaneous rate of change that would equal the average rate of change for at some point on the interval. So let's say that maybe c is here, let's say, so that tangent line has the same slope as the secant line at least once on that particular interval. It looks like there might be another one. But anyway, that's the mean value theorem for derivatives. And so what we're going to look at now is the mean value theorem for integrals, which is known as the average value of a function. So first of all, let's think about a particular function. Let's say that we take g of x, and maybe g of x looks like this, something kind of generic. And let's just say that we're going to look at the interval a to b again. And if we were to try to figure out the average of g, g represented something that we wanted to average, whatever that might be. G was the height of some mountainous region, and we want to know what is the average height. Well, what we would do is we would take the g values on this particular interval. So we would take a g value and take another one and take another one and take another one, and so on. And you can see that there's maybe a little bit of space between these values, but we're kind of pretending like this is infinitely skinny and there's really not any gap at all. And we're just taking all of the g values at every single one of these little spots over and over and over again, and we're adding them all up. And then what we're going to do is we're going to average them by the number that we have. So over here in our first fraction, we have f of x sub 1. That would be just the very first one that I did. F of x sub 2, that'd be the second one, and third one, and so on, all the way out until the nth one. So if we had n of these sample points kind of from g of x, the more the better, we would divide by n, and that would give our average. So just like anytime we've averaged something, we would add up all of the items, divide by how many items we have, that gives us the average. Okay, we're going to connect this to our definition in integral form. So first of all, kind of back up to the beginning of chapter 5. Remember how we talked about delta x, and that was equal to b minus a over n? Well, if we were to solve this for n, we would get n equal to b minus a over delta x. Okay, I know this seems really random, but this will come into play in a minute. The other thing that we want to mention is that we're going to think of this as an infinite sum. Okay, so I'm going to write this as the sum from I equal to 1 to n of f of x sub I. And we've written this in a similar way in beginning of chapter 5, where we're just, if I is 1, we have f of x sub 1. If I is 2, we have f of x sub 2. If I is 3, we have f of x sub 3, and so on and so forth. So I'm just writing that as an infinite sum. Okay, let's add them all up. So what I'm going to do is I'm going to take this fraction right here. Actually, I'll highlight this. So I'm going to take all of this and I'm going to combine it with that. So in other words, well, and this, I suppose. I'm going to sort of combine all these together. So what I'm going to do is take the numerator, I'm going to write it as a sum, as a series, and I'm going to take the denominator, I'm going to write it in terms of delta x and b and a, okay? And remember, this is calculating our average value. And you know what? I'm actually going to go back and I'm going to make this f of x. This doesn't matter a whole lot, but I think everything below on the page is in terms of f of x, so we might as well make it f of x. Okay, so we're going to call this the average of f, so that the average height, whatever we might calculate there. So we have the sum as I goes from 1 to n of f of x sub I, and that is divided by n. So all I'm doing is I'm taking my initial fraction, which again should be relatively intuitive. We're taking the height along f many times, exactly n times, I suppose, and we are going to add them all up. And then we're going to divide, that by n to give us the actual average. Okay, I'm going to make my substitution for n now. So I have my series, then n is going to be written in terms of b, a, and delta x. So my denominator is b minus a over n, and that is equal to, I'm just going to oh, not n, I'm sorry, b minus a over delta x, and that will just be rewritten as a more straight or kind of common fraction rather than a complex fraction. And I'm going to write it as the series from 1 to n of f of x sub x, I'm sorry, f of x sub I multiplied by, I'm just going to move that delta x like that, divided by b minus a. So all I'm doing here is I'm just rewriting, over and over again. Okay, we're going to let the number of function values we're analyzing go to infinity. So we are going to let n go to infinity, and we have our series from I to n of f of x sub I. Basically, we're just making this a very, very, very accurate assessment of, and I should have done this, I'm sorry, this is the average of f. And then we will divide this whole thing by b minus a. Okay, so we've just done a lot of algebraic manipulation at this point. Now, if you do remember back to chapter 5, this limit notation of a series is equal to a definite integral from a to b. That's just the definition from a Riemann sum to a definite integral. So we're going to write the numerator as the integral from a to b of f of x and dx. And of course, we still have the b minus a. If you remember from AB calculus, this was our formula for average value that we kind of just gave people. We didn't really develop it too much, but that is technically now, and I'll just rewrite the average value from the left side. I'll rewrite it over here on the right side. So this is the definition of the average value of f. So you can memorize that. Now, this works for, if I want to find the average value of velocity, for example, I can then average velocity through this formula. So it's a very valuable, useful formula. Now, if we solve this for the definite integral below, we get the average of f multiplied by the difference between b minus a. This has significance geometrically, and I've mentioned this before in class. I always talk about this in AB calculus as well. But if you were to take, for example, I'm doing my best job here. Just forgive the sketch, but I'll try to get close. So if we take a function, sorry, f of x, and we go from let's say a to b like this, okay, and that will give me, oh, that's kind of a bad point. Let me move a over just a little bit so that I'm trying to give you guys a nice picture of what's going to happen here. So I have, let's say that this is a right there, okay? And then B is maybe up here. So I'm exaggerating this a little bit so I can get a better picture of what's going on. Okay, if I was to take a look at the area underneath the graph of F on this region, okay, it looks something like this. You guys have done that many, many times. That is the integral from a to b of f of x dx. Okay, that's the area in red there. Okay, let's say that my average, and again, I'm going to sort of ballpark this, okay? So let's say that my average is here or so, okay? Just roughly speaking. And that would be my average height over that interval. I have a lot of points that are kind of similar here. Maybe I'll use the pointer. So if I go across here, these are all relatively similar. This is a little bit more extreme, so it might put my height around there. Let's just pretend like that's accurate, okay? If we were to take that average height and we were to sort of force the function into that particular height for the entire interval from a to b, we would form this rectangular region, okay? Now, if that truly is the average, then my area of that rectangle is going to be identical to the area of the red. Now, again, you have to sort of forgive my picture, but if you notice, there is some area that is in the rectangle but above the graph of f, and there's some area in the graph of f that is below the rectangle, and the issue with that is that that rectangle balances it all out, so to speak, at the average height, and those areas are the same. So what is the area of that rectangle? Well, that area is the average value of f multiplied by the distance between b minus a. Well, guess what? That is the exact formula that we end up getting just geometrically, okay? Another picture you could think of in your head, I always give this example, is that you are looking at the side of a fish tank, and the fish tank is filled with water. And so you're looking at the side profile, which means it's just one, it's just on a plane. It is not in space. And let's say that someone was to take the fish tank and sort of jostle it from side to side, causing the water to wave and move. And let's say that you were to take kind of a picture of that water just at a split second. The water would be all wavy and all kind of, it would be sort of a random graph. You would see the side of it like this. Maybe it would look like this, okay? If you were to let the water settle out, the water would all settle out to, some kind of relatively flat spot. That would be the average height of the water in the fish tank. So that's the idea of average value, is that you take your kind of wiggly function and you let it just sort of settle out at whatever average height it should be, and that is the value that we find through this calculation. Okay, so we're going to go on to the next page now and take a look at a little bit of this. All right, now ironically, we have one example in our notes, and believe it or not, it's not even on the average value. So this has to obviously be updated. This is on the mean value theorem for a derivative. So I'm going to do the problem, but I will also jump into some of the examples and show you some average value, just so that I don't leave you hanging when it comes to practicing some of these. But this is the mean value theorem for derivatives. It says let f be the function f of x. For what value of x on the closed interval 0 to 5 does the instantaneous rate of change, right there, that's the derivative, of f equal the average rate of change? Now, okay, there's an average in there, but what I'm going to do is I'm just going to calculate the average, which is pretty straightforward. So the average, the average rate of change, by the way, the language is really important here. So the average rate of change will be f of 5 minus f of 0 divided by 5 minus 0. So let's go ahead and calculate that. So we have f of 5, which is going to be 5 cubed, so that's 125, minus 2 times 5 squared, that's going to be 50, plus 5 times 5 is 25, minus 16. So that's going to be f of 5 minus f of 0 is just negative 16. And it's divided by, of course, 5. The 16 and the negative 16 cancel clearly, and we have 125 minus 50 plus 25, that's going to be 100, and that is divided by 5, and so we get 20. So that's going to be the average rate of change. Now, if it said the words average and the rate of change was taken out and it said average of f, okay, that's now this, right? So this is going to be a little bit different, even though the wording is really similar. So you want to make sure that you're cautious about the wording and that you read the problem correctly, because that's going to obviously change some things. Okay, that's the average rate of change. The instantaneous rate of change, so we'll just do instantaneous rate of change, is the derivative. So that's going to be f prime, which is 3x squared minus 4x plus 5, and we are going to simply figure out when those two are equal. So we're going to set those equal to each other. This is going to give us 3x squared minus 4x minus 15 equal to 0, and we'll go ahead and factor this guy out. So that's going to be, let's see, minus 3 and plus 5. Now, we do get negative 5/3 and positive 3, but notice that the only value we can claim from the mean value theorem is going to be on the interval itself, which is x equal to 3. Okay, I'm going to try to communicate one of the big connections here that we need to make with averages. So there's a lot of different, I kind of hinted at it on the last example with average rate of change versus average of f kind of thing, but Anyway, if you're trying to find the average velocity, so if that's our goal, okay, our average velocity, there's a couple ways we can do this, and I'm going to try to make the connection between what we've done in the past and then obviously what this concept is here. So if we're looking at the interval from time 1 to time 2, or t sub 1, t sub 2, if you're given position, so let's start with this, okay? If given position, let's say that the position is s of t, okay? Let's say that we have a position graph that looks something or other like this. The position s for time t, and maybe it is, I don't know, let's do something like this, something kind of boring. And we're going to go from time 1 to time 2. So we're here and we are here. The average velocity is going to simply be the slope of the secant line that goes through those 2 points. So your average velocity, we'll do, let's see, sorry, let's do this. Let's do, well, no, I'll change it, sorry, I'll go back. So we'll do average velocity equal to s of t sub 2 minus s of t sub 1 divided by t sub 2 minus t sub 1. So that's going to be my calculation. Completely fine. Don't think I'm going to say, well, yeah, well, but if, no, really, if you have all of that information, then that is all you need to do. Okay, that's it. Now let's say that we have the velocity and maybe we have no way of getting the position for some reason. So if we're given velocity, and again, maybe the antiderivative to find the position is really, really, really ugly or very difficult to analyze, well, then we might be stuck here. And so let's say we have a graph of velocity. This will be v, this will be t. Pretend like these are connected. I'm not going to get too far into the weeds with this, but let's just say that your velocity is I don't know, something like this, okay? Something a little bit different. And again, don't overanalyze the connection between these two. Let's say that this is t sub 1 and t sub 2, and if you wanted to find the average velocity, you would then go up and find a velocity, and then you would go up and find another velocity, and then another velocity, and then another one, and you'd add them up. You do the average value, right? So the average velocity would be 1 over t2 minus t1. This is the formula we just developed. T sub 1 to t sub 2 of velocity. So we would total up all of those velocities and divide by our interval. Well, guess what? These two items are deeply connected, and they're connected together. Oops, sorry, we'll do this. There we go. By the fundamental theorem of calculus. So let's see why that is, or how they're connected. Well, let's just take the one on the bottom here, okay? So if we take the one on the bottom, and we say to ourselves, all right, how would we calculate this? Well, and I'm going to rewrite it like this so that we have just a better setup. Okay, so we have 1 over t sub 2 minus t sub 1, and if I was to analyze the velocity using the fundamental theorem, I would do the antiderivative, which is s of t, and I would evaluate it from t1 to t2. So of course that would give me, here's my average again, okay, that would give me s of t sub 2 minus s of t sub 1, and guess what? That is identical to what we did up here. So those two formulas are completely connected through the fundamental theorem. And the idea here is that if you have, for example, number 1, the position, okay, we'll just call this one scenario. If you have the position and you need to find average velocity, just find the slope between 2 points. If you have the velocity, kind of scenario 2, and you can't find the position or it's too cumbersome to find the position, we'll then just calculate using the average value function using the integration that we just talked about in this particular section. Okay, let me show you a couple examples. So like I said, the notes didn't have very good examples. Here's some practice in the same section in your book. So this is page number, I believe it's 48. And I'm just going to go over 2 of these. I want to leave some of them for you to try as well. So it says find the average value of cosine Sometimes it's not quite as obvious as that. They may not use the words find the average value. If it says find the average of cosine, that would be the same thing. But either way, here is our average value calculation through integration. And so the antiderivative, well, actually, let's do 1/8 first. The antiderivative is, of course, sine of x, evaluated from -3 to 5, which is sine of 5 minus sine of -3. Okay, so what we get here is, let's just make it sine of 5 minus sine of -3, and then all divided by 8. And if you notice, that's not an answer. What they're doing to you is a little cruel, actually. Remember that sine of x is an odd function. So it looks like that. That means that by definition, sine of -x is equal to negative sine of positive x. That would be the definition of an odd function. Okay. What that means is that sine of -3 is actually the same as negative sine of +3. And so therefore, you would get option E. Now, most people would probably get that answer correct because they would think to themselves, oh, I see, this negative just comes out here and we can factor it out and we have a plus. No, you got really lucky because that's not the reason that it's a plus. The reason it's a plus is because sine is odd, and therefore, by definition, it would be turned into a plus in this case. Okay, let's take a look at one more. So we're going to do the average value of this function on the interval 0 to 2. So we have 1 over 2 minus 0 of the integral from 0 to 2 of our function we're averaging. Okay, this is a u sub, so let's just sit here and analyze this for just a second. So we're going to let u equal x cubed plus 1 and du equal to 3x squared dx. We'll move that 1/3 over. Okay, so we have this integral in terms of u, which is u to the 1/2 power, or the square root of u, either way. That's going to be 1/3 times 2/3 times u to the 3/2, which is 2/9 u to the 3/2. Okay, so if we put all that together, now don't forget the 1/2 that you see in the original. So we have 1/2 times 2/9. That's going to give us a total of 1/9. And we have u, which is the same thing as x cubed plus 1 to the 3/2 power evaluated from 0 to 2. So we have 1/9 times 2 cubed is 8 plus 1 is 9 to the 3/2 minus 1/9 times 1. And this gives us 9 to the 3/2 is 27 over 9 minus 1 over 9. And so we get 26 over 9, which is option A. So there's average value. I hope that was helpful. There are some more to practice, and we will do more in class. Thank you.